As was discussed at the end of the last lecture, you can take a cyclic process on a PV diagram and make a machine out of it. There's a number of different cycles that you can go through, the most famous of which is the Carnot cycle, in which you take a piston full of ideal gas through a series of isothermal and adiabatic expansions and compressions in order to get out work, mechanical work from the system. In this case, as always, the mechanical work will actually be equal to the amount of area that's contained within the cycle, so below the top path and above the bottom path contained in the middle. Inversely, you can run these same types of machines backwards, and instead of getting work out, you actually put work in. And why would you want to do that? Well, if you did that, then you could actually transfer heat from the cold reservoir into the hot reservoir. And this is actually the basis for heat pumps, which maybe you use in your house in order to keep it warm. And in that case, the inside of your house is the warm reservoir and the outside of your house is the cold reservoir. And you don't really care if you make the outdoors colder, especially in the winter time, but you do care that you're making the inside of your house warmer. Another type of heat pump, or that's used in reverse, in this case we're more interested in the cold part, is your refrigerator. So the inside of your refrigerator is the cold reservoir, and you can use mechanical energy to pump out to pump out the heat from the inside of your refrigerator, and you expel it out the back. And if you've ever noticed, the back of your refrigerator will actually have a warm air blowing out of it. That's because the inside of your house is actually the warm thermal reservoir, which you're dumping more heat into. And it really does use a pump. And in fact, when your refrigerator turns on and makes that funny noise in the middle of the night, that's because the pump is turning on in order to continue to cool the refrigerator on the inside. So how does this work? So basically you have a piston, which is the pump, which is the ideal gas, and you could mechanically move the hot reservoir to the piston, causing the piston to rise. And again, you're doing work now against the outside system. You can then move the hot reservoir away, move the cold reservoir in. That will cause the gas to contract. And you're basically doing work in the opposite direction. Then you can just recycle this over and over again to cause the piston to move up and down. Piston inside of your car is kind of similar, except for in that case, you spray gasoline and with air into it, and then you explode the gasoline, and that's what causes the piston to push up and do the work. For all of these machines, you can think of a very kind of straightforward way to think of the efficiency of the machine. People are very hung up on the efficiency of machines, especially as we are trying to create greener and greener machines. What we want is this efficiency to increase. And we look at the efficiency per cycle of the piston, and what we really want to get is more work out for less heat going into the system. And so we want delta W to be as high as possible and delta Q to be as low as possible. Of course, if you had a perfect engine that didn't dissipate any energy at all, which is impossible, you would get this efficiency equal to 1, which is 100% efficient. So the efficiency is in a percentage. The cycle I'm showing you over here, the Carnot cycle, actually has one of the highest efficiencies possible, but it's still nowhere close to 1. And you can calculate it. It's very straightforward. Let's talk about another type of engine that actually is used in biology and that I use in my research, which is a kinesin motor protein. Kinesin motor protein is a little tiny nanomachine. It uses ATP to walk in a hand-over-hand manner. And we actually know quite a bit about this machine, and we actually know enough about this machine in order to calculate its efficiency. So I thought that would be fun for you to do here in the lecture instead of making you do it in class, since I've been giving you some really hard warm-up problems lately. This could be an example of an estimation problem. So let's do this estimation problem. So what we need is the top part here of the efficiency, which is the work done for the cycle. In this case, we're going to have the cycle be a single step, which moves the back head to the forward head. It has been measured, so the work done by this, we can actually directly measure the force and the displacement of the single motor. So we can measure the work for a single step. We know actually that the force is 5 piconewtons and the displacement is 8 nanometers. When we put these together and then convert into newtons from piconewtons, which is 10 to the minus 12, and we convert into meters from nanometers, which is 10 to the minus 9, we get that the work done by a single step of a kinesin is 4 times 10 to the minus 20 joules. This is on the same order as thermal energy if you just multiplied kb times temperature. This is about the thermal energy, but it's actually slightly higher than that. Now we want to figure out what the bottom term is, the change in the heat, and we know that each step takes 1 ATP. And I was able to find in a reference online doing a PubMed search that 1 ATP is about 7 kilojoules per mole per second, and this was measured for a different motor protein, the myosin motor protein, which is found in your muscles. But since they use the same idea and they both use 1 ATP per step, then we can kind of use the same idea. So let's convert this, and it should be on the same order of magnitude. So let's convert this. This has got funky units. It's got moles and it's got seconds in it. So we need to make some reasonable estimates to get rid of some of these weird units here. So let's focus on that. We've put our delta W away. We get 4 times 10 to the minus 20 joules for that. We just put that to the side. Let's just think about this delta Q. First, we're going to get away from the kilojoules and put it into joules. It's 7,000 joules per mole per second. And then we're only talking about one molecule here, and so we can convert the moles into molecules or number of motors using Avogadro's number. So now we get 1.2 times 10 to the minus 20 joules per second. Now this is pretty good. We're actually on the same order of magnitude, but we need to get rid of this seconds, and so we need to think about this a little bit. There is a natural rate for kinesin when it's under no load. It actually walks at 1 micrometer per second approximately, anywhere from 500 nanometers a second to 1 micrometer. This is a good round number we can use. We can convert it into nanometers, which will give us 1,000 nanometers per second, not micrometers, sorry about that. And then we know that 1 step is 8 nanometers as we used earlier. So this tells us that we'll get about 125 steps per second. And we're only interested in 1 step, and really we need to multiply this by a time, so we need to figure out the time of a single step. So we want to know, how long does a single step take? Well, we know that 125 steps takes 1 second. We can just invert this and find that 1 step takes 1 over 125 steps per second, which is the same as 0.008 seconds per step. That is really, really fast. All right, so now that we've used that, we can multiply this 1.2 times 10 to the minus 20 joules per second times the single time that it takes for a single step, and we get 1.5 times 10 to the minus 18 joules. Now we have both of our components to find the efficiency. We can plug them in and look at change in work over the, or the work done over the heat that's added, and we get 2.7 times 10 to the minus 2, which is 3% efficiency. Now, that's not so bad. It's not great, though, especially when we compare it to other real engines. For instance, the efficiency of the engines inside of a nuclear power station that generate our electricity is about 30% efficient. So maybe making a power plant out of a bunch of kinesin motor proteins isn't necessarily the best thing for us.